So in this video, we're going to be looking at qualitative analysis, and we're going to start off with halide ions. Now, halide ions, they're just going to be the negatively charged ions formed from our halogens being reduced themselves. We know, of course, we can end up with chloride, we can end up with bromide and iodide. They're the ones we're interested in A-level chemistry, and these actually have a colorless appearance compared to, of course, our aqueous halogens, which are going to be pale green for chlorine, bromine is going to be orange, and then iodine is going to be brown itself. Now, when we look at these, right, we need to be able to find a way to actually find the presence of these ions, and we can actually do the same test from GCSE, where of course we do the silver nitrate test for halide ions. Now, the first thing that we need to do is, of course, we need to add some dilute nitric acid, and what that will do is it will get rid of any false positives that could form, like carbonates forming a white precipitate for silver carbonate itself. We would add then silver nitrate solution, and we would end up with the silver ions actually reacting, where the nitrate ions, they're going to be our spectator ion, and we end up forming a silver halide precipitate, which of course has a formula of AgX, where X is going to be any halogen. Now, of course, we end up with different colors for our precipitates, and a precipitate is just a solid suspended in water, where we can end up with, for silver iodide, we can end up with a yellow precipitate, which you can see over here. For silver bromide, we can end up with a cream precipitate, which is quite hard to distinguish between the yellow one in some cases. And then again, we've got here white precipitate, and that's going to be for silver chloride itself. And that's basically what tells you which halide ion is going to be present in solution. Now, sometimes it might be a bit difficult to tell the difference between the two, like how we mentioned before. We've got a yellow and a cream precipitate over here, and what we can actually do is we can add some ammonia solution. Now, let's see if I were to tell the difference between a cream and a yellow precipitate, in other words silver bromide and silver iodide. What I could actually do is I could add some concentrated ammonia solution, and our bromide precipitate would actually dissolve, and our yellow precipitate would not dissolve because it's insoluble in concentrated ammonia solution. So that's how we can tell the difference between these two. What about between a white and a cream precipitate? Well, what we can actually do is add dilute ammonia rather than concentrated ammonia solution, and we would end up with our silver chloride precipitate that would dissolve, but then of course our silver bromide precipitate wouldn't dissolve itself. And that's how we can tell the difference between all of them, just to be sure. So moving on then, right, we can actually refer to all of these as precipitation reactions, and a precipitation reaction is basically when we take aqueous ions, two solutions, we react them together, and what we do is we form a solid precipitate itself. And a precipitate, again, it's just going to be a solid suspended in water. We don't mention anything weird like milky creamy solution or anything like that. We just call it a precipitate if it's solid suspended in water, or a solution if of course we've got an aqueous solution itself. Now, looking at the ionic equations we can form, if we were to of course deal with the chloride, bromide or iodide ion, we would form silver chloride, silver bromide and silver iodide. For of course our ionic equation, we get rid of any spectator ions, so I end up with silver, which is going to be plus, we end up reacting that with chloride, which is of course going to be aqueous, and then we end up producing silver chloride as our solid precipitate itself. For the next one, again, we've got silver, which is going to be plus, it's going to be aqueous as well to make it a precipitation reaction, and that's going to react with of course bromide. You can see over here I've got rid of my spectator ion of nitrate in silver nitrate, and then of course whatever is attached to bromine itself. So if I've got, let's say, magnesium bromide, sodium bromide, doesn't matter what it is, if I've got bromide ions in there, that's all I'm interested in. I get rid of the other spectator ion. I end up producing silver bromide in this case, which is going to be a solid. Same thing again for silver iodide. I end up with silver ions, which are going to be aqueous as well. They react with iodide ions, which are going to be aqueous, and we end up producing our precipitate, which is going to be silver and then iodide as solid as well. We end up with 1, 2, 3 equations that we need to remember for the exam, as well as their color, where of course we end up with silver chloride, a white precipitate, silver bromide, a cream precipitate, and silver iodide, which is going to be our yellow precipitate as well. Now again, remember we mentioned that of course, how do I tell the difference if I've got silver chloride or bromide? Well, I add some dilute ammonia solution, and if I've got silver chloride, it will actually dissolve, the precipitate would dissolve. If I have silver bromide, it won't dissolve. We're about testing the difference between silver bromide and iodide because they can look very similar. Well, we would add some concentrated ammonia solution, and our silver bromide precipitate would dissolve, and our silver iodide precipitate would not actually dissolve itself. It's going to be insoluble. So moving on then, right, I've got tasks for you to do. Feel free to pause the video, have a go at the following question, and resume once you're ready to move on. So yeah, in this question, we're told silver nitrate solution is added to a beaker of solution containing sodium chloride, sodium bromide, and sodium iodide. So basically what I'm actually dealing with is chloride, bromide, and then iodide ions. Got rid of my spectator ion. We're told after our silver nitrate is being added, which is going to contain our silver ions itself, because we're not interested in nitrate, we added dilute ammonia solution, and then the resulting mixture is then going to be filtered, right? Now, if I were to react chloride, bromide, and iodide with silver nitrate, I end up making silver chloride, I end up with silver bromide, and then I also end up with silver iodide. Now, if I were to add dilute ammonia solution, the silver chloride would dissolve, but the silver bromide would actually not dissolve. It needs to be concentrated. Silver iodide would not dissolve as well. It wouldn't dissolve in concentrated or dilute ammonia solution. And we've got to think about the practical that they've done over here now. Now we're asked to state the compounds that are contained within the residue on the actual filter paper itself. Now, if we were to think about it, right, we've got a conical flask, and in that conical flask, we've got a funnel and some fluted filter paper. Now, of course, we're going to pass this mixture through our filter paper, and in terms of the insoluble stuff, the solid stuff, it's going to be stuck on the actual filter paper, while in my actual conical flask, I'm going to end up with my aqueous solution containing whatever remains. And in my aqueous solution, after I've done filtration, I'm going to end up with, of course, my silver chloride precipitate that dissolves in ammonia solution. So I end up with, of course, that flowing through my conical flask, and then in the residue I'm actually only going to end up with what's left over, the insoluble stuff, which is going to be silver, and then it's going to be bromide, and then I'm also left with silver iodide itself. So there is my answer for that one. In the next one, they do the exact same thing, but this time they actually deal with concentrated ammonia solution, and we know out of silver chloride, silver, and then it's going to be bromide, and then silver iodide, we end up with silver chloride and bromide dissolving. So that's going to go into, of course, our conical flask, but the silver iodide is not going to dissolve, so that is actually going to be in the residue on the paper itself. So the answer is silver iodide for the next one. So moving on then, why do we actually use nitric acid before we actually do the silver nitrate test? Well, it's to avoid false positive results. It's to remove any carbonates that might be present, and they could actually produce, if they are present, a white solid, a white precipitate, which of course would mislead us into thinking we've got a silver chloride precipitate present. Now, of course, we do this, we get rid of course, our white precipitate by taking our nitric acid, which is going to have, of course, H+, and that's going to react with, of course, our carbonate ions, and we end up producing carbon dioxide gas, and then we end up producing water as well. So, of course, we've got our aqueous H+, aqueous carbonate ions, and we're going to get rid of our carbonate ions by turning it into carbon dioxide gas, and then we end up with water as well, an equation that we need to know. Now, let's say if we didn't use any nitric acid, right, what would actually happen? Well, instead of our silver chloride precipitate being formed, we would end up making a silver carbonate precipitate. So what we would end up with is, of course, our silver ions, Ag+, which is going to be aqueous again, and we're going to end up with two lots of them reacting with our carbonate ions, CO3 2 minus, that's going to be aqueous again, and what we end up with is a silver carbonate solid, and that silver carbonate solid is going to be a white precipitate, and of course it can be mistaken for the silver chloride precipitate. So it gives us a false positive, a misleading answer to saying that, of course, we've got chloride ions present in our solution when we actually don't. Now, why do we actually use something like nitric acid? Why can't we actually use H2SO4 or HCl? Well, when we look at H2SO4, we've got the sulfate ion present there, and in HCl we've got the chloride ion present there, and this could actually lead to some more false positives where we end up producing silver sulfate and silver chloride, which are going to be white precipitates as well, making us think that we've got silver chloride and hence chloride ions present in our ions mixture, when in fact we might not actually have that. That's why we call it a false positive again. So why do we actually use nitric acid? Well, of course, we've got nitrate ions in nitric acid, which is going to be HNO3, 3, and we also have nitrate ions when it comes to our silver nitrate solution itself as well. So we can see, of course, we don't actually interfere with any of our ions itself. But let's say if we did actually use something like sulfuric acid, what would happen is of course we would end up with 2 lots of silver ions, and they will react with, of course, our sulfuric acid, so our sulfate ions, and what we end up producing is of course silver, and then it's going to be sulfate itself as well. Now again, I need some state symbols over here, so I've got solid there, and then I've got aqueous over here, and then I've got aqueous over here as well. So it's another precipitation reaction, but not one that we want to happen. Now what about if I were to use hydrochloric acid? Well, we know, of course, the silver ions, they will actually react with our chloride ions just like before, and we end up producing our silver chloride precipitate, which is what we don't actually want. So yeah, again, we want to avoid false positives where possible in qualitative analysis. So moving on then, right, that's one of our tests done. That's going to be the test for halide ions. There's 3 more tests that you need to be able to do, and of course they're going to be in order of carbonates, sulfates and halides. Now when it comes to carbonates, right, you would add some dilute nitric acid, and what you'd expect to see is fission from the carbon dioxide being produced if you've got a carbonate present. Now the reaction actually goes like this, where of course you've got carbonate ions in terms of an ionic equation, and they react with 2 lots of H+, which is going to be aqueous as well, and you end up forming carbon dioxide, which is going to be a gas, and then you also end up with water that is a liquid as well. Now in terms of that equation, you need to know, of course, the observation is you see fission, that confirms the test for, of course, a carbonate ion. Now if you were to look at, let's say, testing for sulfate ions, right, what you would need to do is add some barium nitrate solution. In some cases they use barium chloride, but we don't want to use that because we don't want any false positives if we're testing for halide ions as well. So that barium nitrate solution, right, that will actually react with our sulfate ions. So our barium 2+ ions will react with our sulfate ions to make barium sulfate, which you know from, of course, module 3, group 2 elements. Barium sulfate is going to be an insoluble white precipitate itself, and there's that one done. If you were to look at the next one, right, you would actually test for ammonium ions by heating with sodium hydroxide. You'd stick a bit of litmus paper in water, make it damp, and then of course you'd wave that litmus paper over the test tube, and if that litmus paper, that red litmus paper, turns blue, you know you've got ammonia gas being produced. You know, of course, you've got ammonium ions present. What would that equation look like in terms of an ionic equation? Well, these ammonium ions would react with, of course, the hydroxide ions. You end up making ammonia gas, and then you also end up with, of course, a molecule of water as well. The water's liquid, the ammonia is going to be a gas, and then of course the hydroxide is aqueous, and then the ammonium ions, they're going to be aqueous as well. So I've just managed to squeeze my state symbols there too. Now in terms of testing for ions itself, we know that we need to, of course, do this in a certain order to avoid false positive results, and the order is going to be carbonates, then sulfates, and then halide ions itself. The reason why we actually do halide ions last is because, of course, if I were to go straight to halides and skip out the actual carbonates itself, I could actually end up forming a silver carbonate precipitate, which I could mistake for, of course, a silver chloride precipitate. If I were to use different types of acids, right, rather than nitric acid, we already know from before, if I used, of course, hydrochloric acid or sulfuric acid, I could end up forming silver chloride accidentally, even though I might not have any chloride ions in there, and then I could end up forming silver sulfate accidentally as well. Now another reason as to why we can actually end up with a false positive for silver sulfate is because we could actually test for halide ions before testing for sulfate ions, and of course if I were to do my test for halide ions and let's say I had sulfate in there and I didn't actually have any halides at all, I would end up with a white precipitate for my silver sulfate itself. So that's another reason, or another way in which you can actually end up with a false positive for sulfate ions. Now the last and final one is going to involve your sulfate ions. Why do you actually test for sulfate ions before your actual carbonates itself? Well, the barium ions that you actually add in the form of barium nitrate to your solution, they will react with the carbonate ions instead of the sulfate ions, and you end up making the false positive again, which is going to be barium carbonate. So again, just some equations that you need to remember member and need to be able to reproduce when asked about false positives. But they are pretty similar in terms of their pattern. The silver ions or the barium ions, they're going to be reacting with the thing that you don't want. So yeah, moving on to the next one then, feel free to pause the video, have a go at the following task, and then resume once you're ready to go over the answers. Just a quick multiple choice question from, of course, the OCR A paper 1 spec. So you've been told here that you've got 3 qualitative tests carried out on a solution of Y itself, and it can be either one of the following: of ammonium bromide, ammonium chloride, sodium bromide, or HCl. Test 1: on heating with sodium hydroxide, a pungent smelling gas evolves which turns red litmus paper blue. So we know, of course, we've got ammonium ions present there, so our answer straight away has to be either ammonium bromide or chloride. On addition of silver nitrate, a cream precipitate is going to form. If it's going to be cream, we know it could be silver bromide itself. So if we know it's going to be insoluble in dilute ammonia solution, we know it's definitely going to be bromine, and then it's not going to be, of course, our chloride precipitate itself. When we add sodium carbonate, there's no visible reaction, so we also know here that we don't actually have any carbonate ions itself. So yeah, now based on this information, we can kind of gather that it's just going to be ammonium bromide. In this question though, we're asked to give the identity of Y itself, the formula of it from observations 1 to 3, and ionic equations for any reactions taking place. Now, of course, it's not told me to give state symbols here, so I'm going to assume that I don't have to give state symbols here unless it's an extended writing question. So in that case, right, I know I end up with ammonium bromide. That's going to be my answer, of course, but then I need equations to show what's happening. Well, the first equation on test 1, we're going to end up with ammonium ions, NH4+, and they're going to react with hydroxide, and they're going to end up forming, right, our ammonia gas itself, and then we also end up with our water as well. There's our first equation. Our second equation, we've actually got our silver ions, which of course they're going to react with our bromide ions, and we end up producing our silver bromide precipitate itself, and there's that one done as well. So moving on then, feel free to pause the video and have a go at the following question, a year 2 style question when it comes to qualitative analysis. Resume once you're ready to go over the answers. So yeah, we've got a student. They conduct a series of tests to deduce the identity of solutions which could contain either ammonium bromide, magnesium sulfate, and ammonium carbonate. We've got some results, and we're asked for the identity of A to C, including any ionic equations for each of these reactions where state symbols are not required itself. Now, looking at our first 2 tests, right, we actually add nitric acid to get rid of any carbonates. If we end up with fission, we know we've got carbonate ions present itself as well. Now, barium nitrate, we add that, of course, to test for our sulfate ions, and then silver nitrate for our halide ions. If we were to look at sodium hydroxide and heat, we actually use that along with some litmus paper above a test tube to actually check for ammonia gas, which is going to be formed from ammonium ions. So that's what the test is for. Looking at solution A to begin with, we know, of course, when we add nitric acid, we end up with fission. So we know for definite we must have carbonate ions being present. But then we also end up with, after heating with sodium hydroxide, ammonia gas being produced, and that turns damp red litmus paper blue itself. So we know, of course, we've got NH4 and then plus, and then we've got CO3 2 minus ions. So we know, of course, the first one is going to be A. If we were to look at B, right, we end up with no change and a white precipitate being produced with the addition of nitric acid followed by barium nitrate. So we know, of course, that's going to contain sulfate ions and nothing else. So we know, of course, magnesium sulfate in this case is going to be B. C, if we were to look at that one, we've got no change with nitric acid or barium nitrate, but we actually form a cream precipitate, and red litmus paper is going to turn blue. So we know, of course, we've got bromide ions here present, and then we also know that, of course, we've got ammonium ions here present as well. So we know we've got ammonium bromide, so that one's going to be C. So in terms of A, B, and C, right, the identities we know, but we need, of course, the equations. So for A, I end up with ammonium, and then, of course, it's going to be in this case carbonate. For B, it's going to be, of course, magnesium sulfate, and then for C, I'm going to end up with ammonium bromide itself as well. Now, in terms of my equations, first of all, I'm going to end up with my testing for carbonate. So I'm going to have a carbonate ion, CO3 2 minus. That's going to react with 2 lots of H plus, and I end up forming carbon dioxide gas, and I also end up forming water as well. The carbon dioxide gas is what leads to fission. The second equation though, because I've got two equations over here, I've got hydroxide ions reacting with my ammonium ions. So I end up with, of course, forming ammonia gas, and then I also end up forming water as well. So there's my second equation there done. Now, normally in the exam, you would get 1 mark for each of these equations, or it would get you onto a certain level when it comes to level of response questions. The next one is a lot easier. We've got, of course, our barium 2+ ions, and they're going to be reacting with our sulfate ions to make the insoluble white precipitate, which we know, of course, is going to be a barium sulfate solid itself. And there's that one done. If we were to look at the next one, similar to the actual top one itself, but we end up with silver ions first. They react with, of course, our bromide ions, and we end up producing silver bromide. And then on top of that as well, we end up with another reaction where we actually produce our ammonia gas itself. So I've got NH4, and that's going to be plus hydroxide again, and I end up producing ammonia gas. And then I also end up with water as well. So yeah, 1, 2, and then 3 more marks over there. And there's that one done.